Well, you couldn't do any worse than you did. We're on page 4. So I gave you that as just a opportunity to earn those points back or whatever, and we'll go from there. Good news is when I put it in, nobody's grade was like crazily affected or anything. It was only 24 points, but that's how it went. So our new unit is on criminal profiling. I actually think the project at the end is kind of cool. So we'll get back to it. I put it at the beginning, just like always, but we'll get back to it. We got to talk probability. So first word up here is probability. Okay, which is the measure of likelihood. Let's see if we can spell that. Of a random event or chance behavior occurring. Okay, so we're going to be talking probability over this next unit. We're going to be going just a little past Thanksgiving with this unit and doing lots of probability. When we calculate probability, there are 2 important pieces. The words for these are sample space and event. The sample space is the collection of all possible outcomes. I'm going to skip a little bit down here when we say that. So the collection of all possible outcomes. So if I come down here to this example that says a probability experiment consists of rolling a single fair 6-sided dice, what is the sample space? What's included in that? If I'm rolling this, what is the sample space? What are all of the possible outcomes? 1 through 6, right? I would enter here, my sample space is 1, 2, 3, 4, 5, and 6. Okay, that's my sample space. So the collection of all possible outcomes is what you're talking sample space. Okay. The event in this case is 1 or more of those outcomes. Okay, so 1 or more outcomes. And I'm going to put in parentheses that we're interested in. Because some people are like, well, what do I choose? Well, if I say what's probably getting a 1, then the only event, the only outcome that I'm interested in is the 1. Okay, and so that's where that comes from. Okay, so 1 or more of those outcomes is the event. Okay, in general, the probability is simply calculated as the event, the number of times the event possibly happens, divided by the sample space, the number of items in the sample space, or what you know about those. Now, the reason it doesn't say the number of items in the event, whatever, because events and sample space can be given to you in percentages and big numbers and whatever. So we just look at it in general terms. Okay. So the note that follows, probability is based on long-term proportions. Okay. In other words, more data means better results. Okay. Probability is based on long-term proportions. So if you have more data, you're going to have better results out of it. Okay? Using long-term data to make predictions is the heart of probability. It's also the heart of like all kinds of different jobs out there. So we wrote our sample space for our first example here. I have a dice so that we can talk about it and whatever, a die, sorry. Dice is the plural. I always do that wrong. What is the probability of rolling a 3? So what can we answer there? 1/6. That's all we're going to go with here, okay? 1/6. Why is it that? Because there is 1 3 on this die, and there are 6 possibilities of what could have happened. So the event is that there's 1 of that event. The sample space is there's 6 of them. It's 1 out of 6. Now, for what we're going to be doing in the next few days, probabilities, percentage, there's all kinds of words, whatever, but probabilities mainly can be written as fractions. They can be written as decimals. In this case, I could say 0.167, okay? Or they can be written as percentages, which any time, and you got to know this in this section, to go from a decimal to a percent, you move the decimal place twice. So you move it over twice and you get to 16.7%. Any one of those answers right there would be acceptable for question B, okay? My suggestion would be you say 1/6 in that case, because it starts off with the fraction is the easiest. Okay, so for that one. So I'm not going to answer all of the answers every time, but you can always answer any of those forms. So what's the probability of rolling an even number? It's be 50%. Think about this. The event is an even number. What are the even numbers on here? Well, 2, 4, and 6, right? Okay, so we've got 2, 4, and 6 are our even numbers. So how many things are in the event? There's 3. So if I'm doing probability, I just click the button and I don't know what I did. There you go. Okay. So my event is 3 out of the sample space is still 6. Okay. You can do it however you want. When you give a fraction, you will always give the simplified fraction. So this would not be a final answer. Okay. So I could either say 1/2 in that case, or like Nick said, he said 50% right away because he knew that half of this, he was thinking 50% in his head. You might go with 50%. Okay, but I could say 1/2 there. I could say 50%, 0.5. Any of those would be the same. Okay, so moving on, flipping a coin. So when you flip a coin, think about just a regular coin. You have either heads or tails. So that's your sample space. Okay, so flipping a coin and getting a tails, what's the probability that that happens? 50%, right? You just have a 1 out of 2 chance. You can do it either way. You can say 50%. You can say 1 out of 2, whatever you want to do there. 0.5. Okay, you have a 1. There's a 1 event that gets a tails. You have 1 tails out of a sample space of 2 different things. Okay. Part B, rolling a 6-sided die and getting a 2. What's the probability that I roll this guy and get a 2? I just did it. Yeah, there you go. It's not 100% like I just did. There is 1 2 on the dice out of 6 possible. So we're just going to say 1/6. Okay. Flipping a 20-sided die and getting a 14. And lo and behold, I found a 20-sided die in my desk. So if you have a 20-sided die, what's the chance that you roll that 20-sided die? So a 20-sided die literally has the numbers 1 through 20 on it. Okay. 1 out of 20. Okay. Let's see if I can do it. That would be pretty impressive. Oh, it's a 19. Close. We'll take it. Okay. I tried. But I had a 1 in 20 shot at doing that. Okay. One of the sides of the dice had a 14 on it. There are 20 sides of the dice. So it's a 1 in 20. Okay. Is it fun? You can try it and see what happens. Okay. The probability of an event is always greater than or equal to what and less than or equal to what? I'm going to fill that in. Probability, if you find a probability, it's always greater than or equal to what and less than or equal to what? Greater than or equal to what? What's the lowest it could possibly be? 0, okay? It's greater than or equal to 0. Hi, Landon. Which matches up with 0%. If you take 0 as a decimal, 0.0 or however you want to do that, move the decimal over, you still get 0%. Okay? So greater than or equal to 0, less than or equal to what? No. Probability. So if I roll a 6-sided dice, yeah, it's 100%. Okay, let's think about this though. I'm gonna put the 100% below. What is 100% as a number? A 1. Good. Okay. Every probability is going to be greater than or equal to 0 and less than or equal to 1. So essentially between 0 and 100%. Okay. That's in general what's happening there. Okay, we have a bag of M&Ms. I don't have any M&Ms with. Actually, I do. Bag of M&Ms contains the colors brown, yellow, red, blue, orange, and green. In a randomly selected package, the proportion of each color is shown below. Proportion is also another kind of word for, well, it could be probability, but percentage there is what they're giving us. Okay. They're asking us what's the probability? So we're taking a chance. What's the probability that you select a candy of any color? What? 100% is what it's going to be. Okay. If you want to look at it as the fact that I have to take 0.13 plus 0.14 plus, I'm going to write it correctly, 0.13 plus 0.24 plus 0.20 plus 0.16. It's going to give you 1 or it's going to give you 100%. But if you really read into this and say, it doesn't matter the color, I just want to select it. I'm going to select the candy. What's the probability of it being any color? It's 100%. Right? What's the probability that you selected a purple candy? Good, 0. There are no purples out there. Okay, don't say none. There's a probability to it. It's 0%. Okay, but it's 0 there. What's the probability you selected a green or yellow candy? So I drew up a candy out and I have green or yellow. What's the probability that that happens? 30% is correct. All you're doing simply there is taking the green, which is 0.16, plus the yellow, which is 0.14, which gives you 0.30. Okay, you can leave it as that, or you can say 30%. A lot of us like to look at these numbers as percentages, so that's what we go to, but you can definitely leave them as the decimals. Okay, so I had a 30% chance of that one happening. Nope. Okay, remember that probability is based on long-term predictions. We just said that. An extensive data collection. Okay, it's kind of like all this probability with COVID going on right now. All they're doing is they're collecting a ton of data and giving you back stuff. The more data they can collect, the better information they can give you. Okay, calculations that we perform based on long-term predictions are called what kind of probabilities? Anybody know? Like if you have all kinds of data, so you have all the probability. No, it's called theoretical. In theory, these things should occur because you have enough data that you know, and you can get to that theoretical probability. However, calculations based on a set of collected data, just a little bit of data, are called, anybody idea there? I said theoretical. The other one? Theoretical probability, and then what? The kind of the idea, experimental. The idea behind this is that theoretically something could happen, but experimentally it maybe didn't. So I had on the dice, I had a 1 in 20 shot of getting the 14. I didn't get it. Okay. So I didn't hit that 1 in 20 chance. If I only do one try, then I experimentally have a 0% chance at doing it. I'm gonna put the phone away. Needs to stop happening. Okay. With this dice, I had a 1 in 6 shot of getting the 2 and I got it. That doesn't mean it's 100% chance of getting it, but experimentally, if I stopped there, I have a 100% chance of getting it too. Okay, so those are a little bit different from each other. So if we look at that information, suppose you ask 500 people to flip a coin 3 times and record the results. You find that 180 of those people received 2 heads and 1 tail. Okay, so we're given some information there. Determine the probability of receiving 2 heads and 1 tail when flipping a coin 3 times. So we're just determining here, and I'm going to throw in that word here. We're going to determine the theoretical probability of this happening. Okay, and then we're going to determine in part B, calculate probability of receiving 2 heads and 1 tail from the based on your gathered data. Okay, so this is going to be our experimental one. Okay. So this is where it gets confusing. Okay. We have 3 different events that are happening. So you cannot simply add up like a head and a tail or whatever. You have 3 different events that are happening. So you do the first coin flip. Okay. What's the chance on your first coin flip of getting a head? Because that's what you want to get. You have 50%. I'm going to write 1 out of 2 just because working with these, it's going to be easier to deal with some fractions here. Okay. So I had a 1 out of 2 chance at the first coin flip getting a head. Then the second coin flip. Let's say we want to get a head on the second coin flip here. What's the chance that you get that? 1 out of 2. It has nothing to do with the first coin flip. Think about that. I flip the coin, something happens. That next time, it's the exact same percentage. Okay. So then on the third one, I need to get a tail because I want 2 heads and I want 1 tail. What's the chance of that happening? 1 out of 2. Okay. So this is the data that's kind of coming into this. And we want to find the probability of all of those happening, okay, across the board. What we are going to do then is take the 1/2 on the first one times the 1/2 on the second one times the 1/2 on the third one. And that's going to give us the probability of all of these things happening, okay, which is either 1/8, or you can give it as a decimal 0.125. I would be careful in these kinds of problems about giving these as percentages because most of us will type that into our calculator as 50 times 50 times 50, and then you're not getting the percentage anymore. So you either want to, when you're doing these, do them as fractions or decimals, okay? And then get to your answer there. So theoretically, that's what we have. Based on our data experimentally, how am I going to solve this? What am I going to do? So the data was given in the problem. What's it going to be fraction-wise? No, not 1 out of 2. We're going to use the data that's given to us. So we asked 500 people. Nick, what you got? Nope, you're thinking too much here. Just read that data that's given to us, yeah? Nope. Go with the data. How many of those people that we polled got 2 heads and 1 tail?
180.
There we go. So 180 got the event that we wanted. So that's my event. They got the 2 heads and 1 tail. Out of what was the sample space? Out of 500, we polled 500 people. The sample space in this case is those 500 people. It's kind of a weird way to look at it, but that's how it goes. Okay. If you simplify it, you can try to simplify whatever. I'm just going to give the decimal. This is 0.36. So we got a 36% chance based experimentally, but we know theoretically that percent should only be about 12.5%. So they can be really far off from each other. Okay. Just like the fact that I got a 2 here was like, I mean, that was a shot in the dark that actually happened, but it happens. Okay. It's not going to happen all the time. So that's going to go. So you're experimentally, but the more that it happens, the more people we polled, the less likely that it's going to be that far away from that 12.5%. Okay. Now, calculating some probabilities, and we're going to talk about the difference between each of these. Okay. You flip a coin 3 times and get heads each time. What's the probability that that's going to happen? So how am I going to do this? So we want to think about this. Is it one event? Is it multiple events? What's happening? What do you got, Nick? Okay, so what are we going to do here? Perfect. We're going back to that half times half times half. It's not that I want 3 heads, okay, in one flip. It's not, I don't have 3 coins and I'm flipping those 3 coins and I want them all to be heads. Okay, it's that I'm flipping the coin 3 different times there. So this is going to be a 1/8. Okay. Letter B, roll a fair die. So there's our fair die and get a 2 or a 3. What's our probability? 1/3. So we had 2 out of 6. Okay. The 2 and the 3, there's 2 events out of 6 total sides of the dice, and that's going to be 1/3. Okay. Now there were 2 different outcomes there that I could have gotten, but it's 1 roll. So in 1 roll, that I get that 2 or 3. So it's not 1/6 times 1/6 there. Okay? I don't want a 2 and then I want a 3. I want to get either a 2 or a 3. Flip a coin. We're going to call this part C here. We're going to refer to it in a second. Change that to a C. Flip a coin and get a heads or a tails. It's an interesting question, right? Yeah, we got. Yeah, it is 100% here. Okay, you're flipping a coin, you're doing 1 event, but you're getting a heads or a tails, and it doesn't matter, then you have 100% chance of doing it. Okay. Letter D, roll a die twice and get a 4 both times. Brayden? Not quite, but what were you trying to do? Perfect. What's that give you? There you go. I knew you were going to get it. Okay. So why did we compute these probabilities? Why did we not compute these probabilities the same way for each example above? Essentially, here's what I want you to give to yourself. For B and C, okay, for B and C, there were multiple outcomes, not multiple events. I'm going to write down multiple outcomes. Okay, the heads or tails in 1 flip, the 2 or 3 in 1 roll. Okay, multiple outcomes. Versus in A and D, there were multiple events. In A, we flipped the coin 3 different times. Okay, in D, we rolled the die 2 different times. Okay, so multiple events there. And that's why we multiplied versus we just increased our number on top. My chart up here looks way better than the one that's printed because it's printed in color. Okay, 2-way tables. This is all the basics of probability. We're going to get into all of this more in depth, but we got to start with the basics. This is what's called a 2-way table. So they took this information, they polled girls and boys, asked them, are you a girl, are you a boy? And do you eat breakfast or do you skip breakfast? And so you had to answer one of those things. Okay, so they put those in there. Anytime you look at a 2-way table, you need to look at the totals of the table because they're going to be played into here. Now you don't necessarily, these are pretty easy ones, but I'm going to put the totals in. Okay, So you want to look at the fact that the total number of girls that were polled was 23. So I'm going to throw a 23 over here on this row. Okay. The total number of boys that were asked was 15. Okay. You want to do column totals. The total number that ate breakfast was a total of 29. The total that skipped breakfast was a total of 9. And you always have a grand total over here. You can add together either one of those that you want to in order to get to it, but you get to 38 total people were talked to. Okay. So those are going to come into play here. Letter A says, what is the probability that a randomly chosen student is a boy? So this is where it comes into play here. A randomly chosen student. So out of, and here's where I start with these, my bottom number is we polled 38 students. So my bottom number here is 38. Okay. Out of those, how many of those were boys? 15. So my probability is 15 out of 38. Okay. Instead of reducing fractions here, I'm going to give you the decimals. So 0.395 is what that would come out to. About 40%. Okay. What is the probability that a randomly chosen student, now these all actually come out the same, but it's going to be important later on. Randomly chosen student. So that means all of the 38 are involved in the sample space. Okay. Eats breakfast. How many of them ate breakfast? 29. So we do 29 out of 38 in that case. Comes out to 0.763. So about 76%. Okay. And what's the probability that a randomly chosen student, so that's out of 38, we're looking at all the students, this one's interesting, is a girl who eats breakfast? How many are there? 16, good. Okay, the girls that eat breakfast, that's very specific, is 16 there. So 0.421, so about 42%. Okay. Now, those are all of the different ideas to just introduce probability. You have, and the first page tells you what you guys have to do each day. Your homework assignment is page 6 and page 7. I will tell you right now that I'm starting to see a little bit of a trend in this class of if it doesn't get done in class, it doesn't get done at all. Or if it doesn't get done in class, it gets copied. And that's not okay. This is a college level class. You can get kicked out of classes like this for things like that. I would rather you just take the 0 on it than copy. I don't want to see it continuing. I'm seeing it way too much now. And there's only 15 of you in here. So it's a very small population. Okay, we need to be very conscious of that, that you're either doing your work or you're not. If you choose not to do your work, you take the grade. Okay, don't copy off of somebody else's. And if you're enabling the copying, you're also part of the problem. And you can get in trouble and get kicked out of school. Okay, I really don't want you guys to get to that point. You guys are all a good group of kids. You're just making poor decisions right now. I need us to be aware of that. Okay, working on this homework. Again, you have some homework to do. So it's something that you want to write down if you need to remember to do it. But it will help if we do our homework, and it will help the grades as we go. Okay, that's what I have there.